Hello dear friends, a great welcome to this series on Idea Statica member. Myself Jarajan P. This is tutorial number 38. Here I will demonstrate how to verify a plate girder that is laterally restrained at the supports and load points using Eurocode EC3. Please also note that the provisions of EN 1993-15 that is very specifically applicable for plated structural elements shall also be respected. So what makes the design of plate girders a challenging task for design engineers is that it is composed of a number of plated elements of large depth and small thickness, making it vulnerable to buckling. So this tutorial will be presented in two parts. Part 1 will cover the modeling aspects and loading, and part 2 will focus on the analysis and interpretation of the results. So let me first of all take you to the problem statement. So we need to design a plate girder that is laterally restrained at load points and also at supports as shown here. So you can see that this is a plate girder, and this is subjected to a uniformly distributed load of intensity W, and we have two concentrated loads of P each applied at points 7 meters and 13 meters for the supports. So the total span of the plate girder is 7 plus 6 plus 7, that is equal to 20 meters. And you can see that here I have drawn some vertical lines indicating the requirements of the internal stiffness as well as the support stiffness, etc. So the material used for the design will be S275 steel. So after a number of preliminary calculations, I have arrived at an approximate cross-section for the plate girder, and it is composed of in fact three plates. So we have two flange plates of 500 mm wide by 40 mm thickness, and we have a web plate of 1170 by 8 mm. For ultimate limit state, that is for the design, the value of W is taken as 65 kN per meter, and the concentrated load at each point is taken as 500 kN. And for the serviceability verification, that is for the deflection checking, W is taken as 20 kN per meter and P is 300 kN. So this is Idea Statica member. So let me give the project name as a plate girder, and I would like to make it in a folder. Let me just give it as a name. It is already there, CMCS. In this girder, in this plate girder folder, I want to make this project. So next thing is that the design code will be the Eurocode, and the material I would like to change it to a S275. So let us take it as S275. S275. Okay. So concretely that is not relevant to us. So here, as you can see that there are various geometries. Our geometry is a very simple straight beam. So span, you can just write as we have already discussed, it has got a span of 20 meters. And the cross section, what we can do is that we can directly define it in the Idea Statica. So let us, for the time being, just create the project. So we just create the project. So you can see that it has already come over here. Yes. So Idea Statica member has already created a default configuration for you. So first, what you can do is you can just change all this, the default settings. For example, as you can see that here we have two columns. Look here. Here we have got one column, and there is one member in the transverse direction. So first, what I'm going to do is I'm going to delete all these numbers. So first, what we can do is we can just go to all these members RM1. So I'll just delete it because I want to keep right now only the analyzed member, and the other members I will add later. So just delete it. Okay, and RM4. Look into the sketch because when you select a member, it will be changed in color like this. So just delete it. Okay, fine. So we have one more member RM2. Delete that also. Okay, so as you can see that we now right now we have only one member, that is the analyzed member AM1. So first let us do one thing. Let us just edit the properties of this AM1. So for that, what you can do is that you can just add a new member. Currently, as you can see, that is HEF 400. We don't want that. So please select. We are not going to have a rolled section here. we will select a welded cross section, right? So we'll select an I girder, okay? And now here you can just go on inputting the dimensions, right? For example, here by default it has shown a girder of a width 200 by 400. That's why it is coding it as a 400 by 200. So let us, based on our this thing, we know that the total depth of it is 1250, right? The total depth of the girder is 1250. So you can write it as just for the identification purpose 1250 by, we know that the width of the girder is 500, right? So please remember that these dimensions are are fixed not just like that. They are being finalized after a preliminary calculations made as per the design requirements stipulated in the course. Okay. So now the height you can just as mentioned, the total height of the girder is 1250. And please remember that the code is specifically gives you what must be the minimum depth based on the span divided by some factor. Normally, span divided by say 15, span divided by 20. These are all the adopted ratios. So you can use those guidelines to come out with a proper depth. That is, I said 1250. And now let us start feeding the sizes of the flange plates. The thickness of the flange plate for this exercise, I kept it as 40 mm. So we can straight away keep it as a 40 mm. So this is a 40 mm, and the width we know that it is 500. So 500, and the thickness of the web can keep it as say 8 mm here, and the material is S275. So look here. So we have the flange plate that is a 500 by 40 mm thick, and we have the web plate that is of a dimension deep 1170 deep and 8 mm thick. So the total depth of the girder that is 1250. So we are satisfied with this size. Okay, fine. Now we need to simulate the vertical supports at each end, right? So the best way to do that is to directly go to the CON11, that is the connection. So means that this is the connection at this left hand location of girder. So here what you can do is that you can add a member, okay, a related member, ended. I don't want the column to extend it throughout. Okay, this is just for the simulation of the support. I don't want to do any kind of a support design here. So what I would do is I would just provide a member, a related, ended related member. Ended means it will stop at the end, and continuous means it will go straight throughout. So we can add in the set direction. Okay, so set. Okay, so now you can see that yes, a member is already added here, a column member is added here. We need to make some modifications, and remember that when we have modified the connection COL1, a member RM2 is automatically generated for us. Now what we can do is we can straight away start editing the dimensions. So here what I will do is I will ensure that the width of this column is good enough to okay to provide a seating for my plate girder of a width 500. So accordingly I will keep the width of the flange for this RM2 also as 500. Okay, so let us just edit it. So we just go here, and for this also what I will do is that I will go for the welded composed, okay, this one. And here what we can do is that here I will keep a size of say 500 by, so this is I will keep 500 by 500. Remember that these sizes are not that much relevant for you, but you ensure that these sizes are such that it allows a proper support connection. Okay, and the total height of this girder of this column support, I assume it is a 500. And regarding the thickness, what we will do is that we will assume a flange of 20 mm thick. Okay, a flange of 20 mm thick. That's good enough. And the width, as you know, we'll assume it as say 500. Okay, we'll assume it as 500. So this is my 500, and the web thickness I will assume it as 6 mm, 6 mm, 6 mm, and I will keep the same as 275. Okay, so you can see that here say 500 by 500. So your plate girder will come and sit over this column. Okay, and you can see that the flange thickness is 20 mm and the web thickness is 12. So this is okay. So now here what I want to do is I want to see that this particular member, okay, now as you can see that my girder, plate girder, okay, it is kept somewhere in between. Okay, now I want to ensure that this analyzed member AM1, it is supported directly over this. Okay, directly over this. So what you can do is that you want to keep a shifting. You know that the total depth of this girder is how much? It is 1250. So it does mean that if you shift this member 625, that's 1250 by 2, that is by 625 mm, you will ensure that this particular flange, it is seated directly above this column. So what I would do is I will go back to my member AM1 and I will feed this EZ offset EZ parameter as a 625, which is my half the column depth. So yes, look here. So now you can see that yes, there's a plate, my plate girder sits directly above the column. Now I also want that this column being shifted towards the right so that this flange will match with this edge. Okay, so what I would do is I'll go back, let me just, okay, I'll go back to my RM2, and in RM2 what I will do is I want to, you know that the total depth is 500. So I want to keep it half the depth again inside. So what I would do is I'll keep my EZ here. EZ right now it is 0. That is why you are having this position. So I'll keep this as minus 250, minus 250. Okay, minus 250. Now look here. Now you can say that yes, this column has, so you can have a look here, right? So this is a plate girder, it is seated directly over the column. Okay, so this means that we have generated the column on the left support. Now let us go for in a similar way, let us go for providing a column member on the right side of the plate girder as well. So similarly what we will do is go to CON2, so indicating this location. In a similar way we add an ended member, and obviously it should be added in the Z direction. So obviously you can see that yes, the member is already added. So obviously the parameters associated with RM3 will be exactly similar to RM2. So in spite of that, let me just edit it. So I can just edit the parameters over here. Okay, or maybe that it is available here also because we have already generated it. It is I 500 by 500. Yes, it is available already. So nothing to regenerate. And we know that it is the shift which we have to keep for this. It is equal to plus 2. In this case, I want to keep it towards the left. So instead of minus 250, you give it as a plus 250. 250. Okay, fine. So the rest is the same. So it does mean that we have generated, okay, the left column and the right column properly. Now we need to focus on the so-called the lateral restraints. Now, so let me just, before that, let me just zoom it. Look here. So this support is also properly generated. Now let us go ahead with the so-called development of the lateral restraints. Now, it is very important for plate girders that you fix properly, that means after calculations, the location of the lateral restraints. Because in many of the plate girders, you will find that if you, for example, suppose that we are going by train, if you look onto the plate girder that is supporting the railway bridge, you will find that the top flange, it is laterally restrained by providing a very effective horizontal plan raising. So the designer has to ensure what must be the spacing between these lateral restraints. Okay, and now in this case, what we'll do is that, as I already told you, we have provided, okay, we have provided a lateral restraint at the support, right? And also we have the lateral restraint at the load positions, right? And the load positions, we know that it is at a 7 and a 13, etc. So what we can do is, now it is very important also that you can also run a buckling analysis without the lateral restraints, and that will also tell you how sensitive is your flange against the lateral buckling. And once you fix the positions of the lateral restraints, please also check the effectiveness of this lateral supports against buckling through a linear buckling analysis. So this has to be done by trial and error. So I have fixed it comfortably now for this girder 4 laterally restrained beams, one each at the supports and one each at the loaded points. So let us start creating these lateral restraints. So what we can do is we can go first select this AM1, okay, and on AM1 we want to create a lateral restraint, okay, fine. So now let us first create, and because we want to have the lateral restraints at 4 points, so first create an intermediate node point. Okay, so it has created, okay, maybe that may not accept 0, so it has created an absolute position 0.5. Now what we want is at this location at 0.5, I want to add a related numbers, and remember that in this case I want the related numbers to be added not in the z direction but in the y direction. Now, so what we can do is that let me just add in the y direction. Okay, so as you can see that yes, I have created a lateral restraint beam here. Just a minute. RM4. Okay, now what we can do is we can straight away go for editing the parameters of RM4. Remember that RM4 is a beam that is added for the lateral restraining of the compression flange of the plate girder. So let us go again edit some parameters. So I think that we don't have a member here. Just a minute. Let me see what are the members we are having here. We are having only HE. So let me add a very simple member because its purpose is just to provide a lateral restraint. I would like to add an IP member. So I will go here and IP 240. Okay, fine. And S275. Okay, this is good enough for me for the lateral restraint. So now let me just zoom it because it's a smaller size one. Okay, look here. Now the problem is I want to add this member. I want to take this member to the top. Okay, currently you will find that the top flange it is almost at the bottom of this girder. So what you can do is we can just so look here. So here you can see that the bottom flange is at a half depth. So it does mean that we have to add, you know that the total depth of this IP240 is 240. So half the depth, that is 120, plus the girder thickness or the height of the girder, that's 1250. So that means we need to move this beam, okay, by an amount of 1370. Okay, now let us just feed this into this. Let's see what happens. 1370. 1370. Yes, look here. Now I have my beam that is directly placed over the compression flange. And obviously you know that this will be able to tie my compression flange more effectively. Now the same procedure we need to apply to all other locations. So obviously we know that we have got other locations. So this is at x is equal to 0.5. Now in a similar way, let us go on adding very effectively. So the same parameters. So what you do is you select the X, there's a AM1 intermediate node, okay, and intermediate node obviously we know that the one is at 7 meters, right? If I remember, let me just check my sketch. It is at yes, it is at 7 meters. One loader point is at 7 meters, so let me just feed it as a 7 meters over here. So now we can move very faster. Okay, at 7 meter I want to have at in the y direction. Okay, so look here. So you can see that RM5 is automatically created. So you can just change the size to IP240 because we have already generated it. And just like in the other example, what you can do is that you can just keep this as at 1370. So this will be 1370. That must be okay for you. Yes, so we find that we have added now a lateral restraint at one location, that's 7 meters. Similarly, what I will do is that I will add another member once again. So go back to OM1. Okay, now generate an intermediate node. Now right now it will be at 13 as the location of the other loader points 13. Okay, and add a member in the y direction. Yes, you can see that we have added a member in the y direction, and that is RM6. Just to go on editing the sizes, that will be IP240, and obviously my F set this will be 1370, just like the other member also. You can find that yes. So we have added, and now what is left is we have to add one more member at the right support. So in a similar way, go back to AM1. Okay, so add an intermediate point, and here what we do is that we keep it as at not at 20. I'll keep it at 19.5. So 19.5. Okay, so I'll just add a relative member in the y direction. So you can see that it is being added. I have got an RM7. Just to change the size as usual to IP240, and then we have an offset of say 1370. Okay, so you can say that yes. So look here, we have generated all the beams that are required for providing us the lateral restraints. So look here, our main member is the AM1, which is to be analyzed, this girder, and we have got two supports, that is RM2 and RM3, and we have got the four lateral restraints, that is RM4, 5, 6, and 7. So now let us proceed for editing or providing the connections between the various analyzed member AM1 and the corresponding related members RM2 to RM7. So let us proceed for editing the connections. So let me select the connections here in one. You'll find that this connection is highlighted. Just edit the connection. Here I want to just add an end play connection. So let me just edit the connection so that the program will automatically switch over to the Idea Statica connection, and that lets you edit the connections. And here I want to just repeat once again that this Idea Statica member is not intended for verification of any connections. So here you can see that yes, it is the connection is highlighted. Here what I want to do is that I want to just provide an end plate here, and in order to simulate a pinned condition at the support, I want to just use one bolt on each side of the flange. Okay, and remember that my intention is not to model the entire connection, but just to simulate the pin connection. So what I do is I just go to the operations, okay, and I just to add the operation, and the operation we have got the end plate, go straight to the end plate operation, okay, and that will okay, you can just add say M20. So for example, say 6.8 M20, because we are not going to verify these connections, just for the analysis purpose we are simulating it. Okay, fine. So we know that it has to be. So look here, it has come directly over to the AM1. I don't want it over AM1. I want to the other member, that is RM2. Okay, so you go directly to the RM2. Okay, fine, and okay, fantastic. So you'll find that there is a host of bolt, a number of bolts that we can quickly change. That's not a big issue at all, and it is connected to okay AM1. Okay, fine, and S275, and the thickness, you can keep it as say for example say the end plate thickness, you can keep it as a for example say 20 mm, right? 20 mm, that's good enough, and bolted. And all these offsets, what you can do is that you can keep it as a 0 0, right? This will be 0 and this will be 0. Okay, this is 0 0. All these offsets I will keep to 0, so that this is just to ensure that my all my end plate it is a flush with this member RM2. Now coming to the boards, what you can do is that I want only say two boards, not this many sets of boards. What you can straight away go over here. The top layer, for example, you can set it over say the minus 250. So this I want to set as a minus 250. I don't want this much of rows. I want only a single bolt 250, and I can keep the left as for example minus 120. These are all calculated dimensions so that the bolt will fit properly. Okay, and the bottom I don't want to fit in this case. It is not relevant to me. And the right one I will keep it as say minus 120 again, minus 120, and I think that the rest of these parameters, let us leave it unchanged. These are all good enough. So now okay, yes, we have M20, the layers 120. Okay, just a minute, and the right. Okay, so now look here. So let me just because you also would like to know what kind of support we have generated. So look here, I have just generated a single bolt connection. Okay, it is just a single bolt connection. Look here, you can say that it's just a single bolt connection. Okay, and the single bolt connection is intentionally created because what happens is if you put a large number of bolts, obviously what happens is that the support will develop, the moments. So I want to ensure that it's a pin connection. So this means that we have generated one connection properly. Let me just save this so that this will be available for me in the connection. So now we know that, for example, if you go to CON2, right? CON2 is this connection. Obviously, this should be same as the CON1. So what we need to do is we just select this CON1, just apply it. Okay, we need not again generate it. It saves a lot of time for us. You can see that whether the same is generated or not. Look here, yes, the single bolt connection I do have. Okay, so you don't have any kind of a problem. Single bolt connection is already mobilized. Now we need to modify other connections, CON3, and CON3 is okay, just a minute. We have CON1, okay, CON2, and the CON3. Okay, so the CON3, it is not relevant to us. Let me just zoom it over here. What is this? Okay, so we can just delete it. It is not relevant to. Okay, this is okay, fine. So now this is relevant to. Look here. This is between the two connections. That is between AM1 and RM4. AM1 is this member and RM4 is this member. That's a lateral restraint beam. So let us just start editing this connection, right? So just edit the connection. Okay, so here I just want to place the two boards. Okay, in order to ensure that this is directly connected with the plate girder flange. So for this, what I will do is straight away go to for the operation, and in the operation there is one operation known as a grid operation. It is over here, I remember. Yes, look here, this is a bolt grid operation. So just select it. Okay, and the bolt grid operation. So okay, don't worry about this. We are going to feed all the data. So fasteners, bolts, item count 2. Now you select what are the members to be selected. Okay, we know that one is AM1. So it is a plate member. So AM1 is already selected. And now coming to the other one, I want to connect it with my RM4, and RM4, remember that we want to connect to RM4 bottom flange. Okay, so okay, the message, the warning is already over. Now it's a matter of just uh, providing the dimensions. So item count, everything is provided, and the origin will be kept as 0, and the positions and the rows. What we do is that we keep it as a -75, -75, and then -100, -100, and then positions, these are all pre-calculated dimensions, -35, -35, and okay, positions, we have to keep it as a -35. Okay, and then 70, 70, and the rest remains the same. So now let us see whether the required bolts are being created. Just zoom it. Look here, it is already two bolts are already generated. That is okay, fine. Now we can just copy this connection for the other parts. Okay, you just save this. Okay, and now it is very easy for us to go ahead. Let us start creating the other connections. So let me just take this a little bit up. Okay, this is already generated. You can say that. Look here, it's already generated. Now it's a matter of just copying. So con3 is over. Now con4 is the connection here, and you can see that which are the members that is connecting this connection. So now we know that con3 is already available to us, right? So we need to just apply it. Okay, so just apply this. We need not to again regenerate it. Look here, it is automatically generated. Okay, now the similarly, let us go for the con5. Con5, go to con3, apply. Okay, so we find that it is so once a connection is generated, it can be easily copied. So this is what we are doing right now. Now finally one more connection is required, that is con6. Okay, go over here, con3, and apply. Okay, fine. So look here, so means that we have generated the all connections, that is the connection between all the related members on the analyzed members are now over. Now it's the time we straight away go for the load applications. And here what I did is that I have generated two loads. One is LE1 that I will use for my don't worry about the ULS and all. I will use my LE1 for the design, and the LE2 I will use for my the serviceability verification. So as you know, this is subjected to three loads. One is a uniformly distributed load and the 2 point loads. So let us start feeding these loads now. So we can say that one, the uniformly distributed load that is acting on AM1, and we know that it is so let us change it to the global. In some cases that may make a change. So we know that it is the intensity that is under the LE1, that is a 65, so 65 kilometer meter. So we just keep it as a -65 kilometer meter. and what I do is that I apply it over the top, and I will just rather keep this as a 0. Okay, so that's all about the uniformly distributed load. And the next what we can do is that we can start adding the concentrated loads at 2 locations. So here I will apply the concentrated load as a line load only, and I will keep that the width of the line load is only 0.2 meters. So it does mean that, or if you remember, our concentrated load was 500, right? So if you convert it into a line load of 0.2 meters, the value will be 500 divided by 0.2. That is nothing but 500 into 5, that's 2500. So let us add another line load here, that's on M1, and obviously we know that this is acting over 7 meter. So what I do is, so 7 meter, I will apply 6.9 and 7.1. 7.1. So you know that it is nothing but a line load spread over 0.2 meters. And this I will just change it to say global. Okay, this I'll change to global. And remember that the intensity is properly entered here. That is, instead of 500, it will be minus 2500. Okay, because we are distributing it over 0.2 meters, and we'll keep it over the top flange, the top, and all other dimensions will keep the same. Okay, and what we can do is that we can add one more concentrated load. Obviously that will be at, it says 12.9 and 13.1, 12.9 and 13.1, 13.1, 13.1. Okay, that's good enough. And what we can do is we can keep it as global, and we'll keep the intensity as minus 2500, minus 2500, and the member axis will obviously keep it as on the top, fine. And all this width will be zeros. Okay, and that's all regarding the line loads and the concentrated loads. And for LE2 it remains almost the same. Okay, only thing is that we have to change the load values LE2. So what I will do is that I will go to LE2, and then I will add the similar values. Okay, I'm not going to repeat that procedure here. I'll add all the required values that is corresponding to the subvisibility limit state. Okay, fine. So after adding this LE2, what we need to do is we need to go into the other very important operation, that is known as adding the stiffness. And this is a little bit elaborate one. So rather than including this, adding the stiffness in this module, what I want to do is that I want to take it to the other part of the tutorial, that is the part 2 of the tutorial, because I want to demonstrate to you some of the important aspects of how to verify whether a particular stiffener is required or not. Because as you know, there are many types of stiffness that is being added to the plate girders. That is normally, in almost all the cases, we need to add what we call as an bearing stiffener, and also we need to add some kind of the stiffness directly under the loads, which act as a bearing stiffness. And also in order to ensure that no shear buckling occurs, we need to also spread all across the length of the girder the intermediate stiffness also. So this is a little bit elaborate one. So I would like to take it to, though it is a part of the modeling, I would like to take the addition of this intermediate stiffness as the next part. Okay, so those who are seeing this tutorial, please also ensure that you also jump to part 2 of this tutorial, so that you witness, okay, all the important steps that are required for the modeling and analysis of the plate girder. Okay, so then till then, bye and have a nice day.